Beneath this airport, there is no land, no stone, no stability, only deep ocean clay slowly giving way under thousands of tons of steel and concrete. Every second, it sinks a little more. And yet, somehow, this became one of the greatest engineering achievements in human history. This is Kansai International Airport, a sinking airport built in the middle of the ocean. On ground engineers knew would fail. So how did Japan pull off one of the most insane engineering projects in human history? By 1980, Osaka's economy was suffocating. Its only airport was trapped, boxed in on every side by a dense wall of residential high-rises. Screaming jet engines triggered brutal legal bans. No flights after 11 p.m. International cargo restricted. Global connections dead. One of Asia's biggest economies strangled by a nightly curfew. Japan needed a radical escape hatch, a runway that could scream 24 hours a day, with zero human neighbors to disturb. So engineers looked 5 kilometers offshore into 18 meters of open ocean and proposed a madness. Build a massive international airport in the dead center of the bay, on an island that did not exist. Japan faced a choice: economic stagnation or impossible engineering. They chose the impossible. In 1987, Japan broke ground. Budget 1 trillion yen. Workforce at peak 10,000 people. Seabed beneath Osaka Bay isn't rock. It's deep, soft marine clay. And clay under pressure does one thing: it compresses. Slowly, continuously, for decades. Engineers calculated the weight of this island would cause 8 meters of total sinking on a structure where 1 centimeter of uneven movement shuts everything down. So before the airport could rise, they had to fix the ocean floor itself. What they did next had never been attempted at this scale anywhere on Earth. Survey vessels moved across the bay, drilling core samples, mapping every meter of the future island's footprint. The data came back exactly as feared: deep, soft, and highly compressible. So marine barges arrived and began driving thousands of thin sand columns into the bay floor at precise intervals across the entire site, each one a drainage channel. As the island pressed down, these columns pulled the trapped water upward faster, controlling exactly where and how fast the ground settled beneath. Because uneven settlement at an airport isn't a maintenance issue, it's a shutdown. One end of a runway drops faster than the other. Shutdown. An underground fuel line shifts out of alignment. Shutdown. A terminal floor develops a permanent lean. Shutdown. With the seabed treated, the next challenge was containing the site itself. Engineers designed massive hollow reinforced concrete boxes, each weighing around 80 tons, to form the outer seawall. Over 1,000 sections manufactured on shore, barged out across open water and placed on a soft, muddy seabed against tidal currents. Divers worked below. Survey teams tracked every movement from above. Every joint between sections had to seal completely. One crack and the entire enclosed area floods instantly. Section by section, over 2 years, the wall grew. When the final piece locked into place, Japan had enclosed a protected area in the middle of Osaka Bay, an empty space in the open sea, waiting to be filled. Now came the part that reshaped 3 mountains. 3 mountains in Japan were partially demolished to source the fill material. Hillsides near Kobe, Wakayama, and Hyogo, excavated on an industrial scale that permanently changed the landscape. At peak operations, 1 fully loaded barge was arriving and unloading into the bay every 15 minutes, around the clock, every day for years. The fill wasn't dumped randomly. Coarse rock went in first to create a stable base, then gravel, then sand, then compacted clay to bring the surface up to final grade. Every layer engineered, every elevation checked. The island was rising, and then the instruments showed something the engineering team had not expected. The island was sinking, faster than any of the models had predicted. The weight of each new layer was accelerating the compression of the clay far beyond the original calculations. Original estimate, 8 meters of total sinking over the life of the project. New projection, over 11 meters. The island would keep sinking for decades after opening, and there was no way to stop it. This was the moment everything could have fallen apart. Facing a problem that couldn't be eliminated, the engineering team made a decision that shifted the direction of everything. They would not try to stop the sinking. They would design the entire airport to sink continuously for decades without ever losing operational function. The worst engineering failure imaginable, a structure disappearing into the ocean, became a deliberate design feature. Architect Renzo Piano was brought in for the terminal. His task? Design a 1.7-kilometer-long building that would continuously change its own elevation at different rates across its full length for the entire life of the structure. Different sections of the island were settling at different speeds, the western end sinking faster than the eastern. A conventionally built, rigid structure would crack within years and fail within decades. Piano's solution? Make the building adaptable by design. Every structural column in the terminal was fitted with a hydraulic jacking system built directly into its base. Around 900 individual columns, each one independently adjustable. As different sections of the island settled at different rates, maintenance crews jack up the lower columns, returning the floor to perfect level. The building doesn't resist the movement beneath it, it absorbs it, column by column, section by section, continuously. On top of that, engineers deliberately overfilled the island during construction, piling material above the final target elevation to account for the confirmed decades of future sinking ahead. The island was intentionally built too high so that after years of controlled descent, it would arrive at exactly the right operational level. The sinking was no longer the enemy. It had become the engineering strategy. This approach, designing for settlement rather than against it, became the global standard for construction on soft ground worldwide. Now they had to build an actual airport on top of all of it. Building a runway on an artificial island in open ocean is completely unlike any conventional paving operation. The platform was still moving beneath every layer being laid. The entire drainage network had to go in first. Typhoon rainfall can deliver enormous volumes of water onto a low-lying island within hours, and there is nowhere for that water to go naturally. Hundreds of drainage channels, pump stations, and seawall outfall systems went in beneath the future runway footprint before a single layer of asphalt was touched. Then the runway itself, 3,500 meters long, perfectly straight. Subbase, base course, asphalt binder, final surface. Each layer in strict sequence, compacted to aircraft-grade density, verified before the next went down. This was not paving a road. It was creating a surface where fully loaded passenger aircraft would touch down at high speed. Day after day, year after year, on ground still slowly moving beneath it. Instrument landing systems were calibrated specifically for Osaka Bay's persistent sea fog, because fog doesn't care how impressive the engineering is. A certified runway, completed on reclaimed land above marine clay, 5 kilometers out to sea. Renzo Piano did not design a conventional terminal. He designed something that looked like a glider that had come to rest on the surface of the bay. Long, low, aerodynamic, with a continuously curved roof, sweeping the full 1.7 kilometers from one end to the other, the longest building on Earth when it opened. That roof was not an architectural gesture. It was a typhoon defense system. Wind tunnel testing confirmed the curved profile caused wind to flow over the surface rather than impact it directly. The same principle that generates lift on an aircraft wing. In a direct typhoon strike, the roof sheds the wind rather than fights it. The structural steel in the terminal alone weighed 70,000 tons. Every single roof truss was custom manufactured. because Piano's continuous curve meant not one standardized component existed anywhere in the structure. Over 80,000 individual stainless steel panels form the roof surface, no two panels the same dimension. Inside, Piano designed the space to feel like a canyon, natural light moving across the full-length interior throughout the day. 200 kilometers of electrical cable run beneath the floors, 70 kilometers of underground baggage conveyor belts, 42 boarding gates, every one reachable without a staircase or elevator. And beneath each of those 900 columns, the hydraulic jacks, working silently every few months, keeping the floor perfectly level as the island continues its slow descent below. An airport 5 kilometers offshore is useless without a reliable land connection. Japan's answer was the Skygate Bridge, nearly 3,750 meters of road and rail stacked on top of each other, crossing the full width of Osaka Bay. More than 200 concrete piles were driven into the same soft seabed that had caused the settlement crisis on the island. Every bridge column was engineered to resist tidal loading, wave forces, and constant marine movement. Bridge deck sections were prefabricated on shore, floated out on barges, and lifted into final position. Each section weighed around 200 tons, and everyone had to land within millimeters of its target, or the alignment of the entire span would be compromised. Both ends were built simultaneously, the mainland side and the island side advancing toward each other across open water. When the two halves finally met in the middle, the alignment error was measured in millimeters. Road on top, rail below. Japan's first double-deck ocean bridge, completed in open water. Japan gets hit by powerful typhoons every single year. Kansai sits in open water with no natural protection from any direction. Engineers had spent years testing the terminal against extreme wind loads. The seawall had been raised and reinforced after storm modeling identified gaps in performance at the outer edge of design scenarios. Over 1,000 expansion joints were built into the terminal, allowing the full building to flex under extreme wind rather than accumulate stress until something cracked. September 4th, 1994, 7 years after breaking ground, Kansai International Airport opened. The first aircraft to touch down was a Japan Airlines 747 arriving from Tokyo. Within the first year, airlines from 40 countries had scheduled regular service to Kansai. Today, a dedicated monitoring room tracks every settlement sensor across the island, around the clock. The island's elevation is checked every single hour. Every few months, maintenance crews move through the terminal, adjusting the hydraulic jacks beneath columns that have settled, returning every floor section to perfect level. The building has been correcting itself continuously since 1994. The island has now sunk over 11 meters since construction began. It will keep sinking, and the airport will keep working. Kansai International Airport did not solve the problem of building on a sinking ocean floor. It made the problem irrelevant. That is the difference between engineering that survives and engineering that endures. An airport in the ocean, sinking every day, open every hour, built on nothing, standing on everything. If you enjoyed the video, subscribe to Project Apex for more stories about impossible engineering, mega projects, and the ideas that changed the world.